Okay. Eh, So that's equivalent to this, right? Yeah. Hmm. Okay. Right. So phi and n are right, always invariant, and I'll just say always invariant. Okay. 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 For any k between hmm, f such that degree of f equals to power k. Uh, Arrow diagrams to represent functions. Right. Okay. Yeah, this one looks yeah, also true to means I can I think see it. Yeah, so it's like if you have a k, then you map one to k to the last k things, and no, no, so no, that would not be correct. So let me just make a guess. So if I take a k, then how do I get a k invariant subset? So yeah, I mean I could just take the first k and map them identically. Yeah, and the rest I have to just ensure that they don't. Huh. Oh, right. Okay, yeah, yeah, correct. So how do you? Okay, so how do you do it? Yeah, that's right. Yeah. Okay. That's okay. Right. Okay. So you want to map k to k plus 1. Okay. N will go to k. Why will n go to k? Oh, okay, right. So that's right. So right. So you send n minus 1 to n and n to k. Okay. Hmm. Hmm. Right. Hmm. Okay. Why? Yes. Now, okay. Wait. So if you take, so what you do is you take these always, and yeah. So again is 2 to the k minus 1. Nice. Right. Yeah. So idea is to take them always and then range over subsets. Good. So that's what you wanted to say. Yeah. Okay. Perfect. Right. And just tell me one thing. So is this number of invariants always a power of 2? Okay. Uh, so it's not. Can it be any number? Right. So you say you found 3, 4. Yeah. Okay. Yeah, that is the question. Check. No. No. Function is not unique. You can count how many of them are there. I suppose that should not be difficult. That may not be difficult because, yeah, but yeah, let's write this question. So, uh, what numbers can number of invariants? Yeah, let's see. So, mm-hmm. Yes, yeah. Huh. Mm-hmm. Let's see. Let's see. So, what was the construction? Huh. Okay. Yeah. Yeah. Right. Okay. Oh, sorry. Oh, right. Because you have to take everything or nothing. Right, right. Yeah. So 2 is always achievable in that way. Yeah. And no, for yeah, and for any n you can get 2 as the number of invariants by that cycle way, right? This one has 4, right? Yeah. 3 is, I don't know how you get 3. Yes, it's possible. That will just increase the number. I don't know because yeah, that will increase the number of invariants. Ha. Yes, yes, yeah, and that way you will get a that will 2 cubed. Okay, maybe. Yeah. Huh. Right. Yeah, that will be 2 cubed. That's what we just did. Yes. Anyways. Yes. 3. Right. 3 is. If you're taking bijections, then you can use the idea of cycle decomposition. Maybe that is what you are doing actually, without writing it like this. And I think 3 does not appear that case. I see, right? I don't think so. Can you get 1 or at least 2? Sorry, yes, right. So it seems like you cannot get 3 also in that way. But that's probably a, let's see. So through this cycle only, you will get um, uh, through the cycles you get 1 invariants. So there are 3. If there are 3 cycles, you get 3 invariants. Let's say these are permutations. But then you have, so this is 3 choose 1. But then you also have 3 choose 2. They are also, because if you take 2, exactly, yeah. And you see, this is always a power of 2. So permutations always give you powers of 2. That's how we have proved that. The permutations will not work, but other functions, I don't know. Let's see. Because there you won't get a cycle decomposition. But you can still break because it will still just be a graph, right? Where every vertex has out degree at most 1. If you think of it as a directed, and that's what you have drawn here. Just you have we have just written them twice. So instead, if we only write the everything once, then we get a graph. And let's try to see. I think that way also you will only get powers of 2. Because yeah, let's see. Because let's draw it as a graph and see. 1, in degree can be anything, right? Because an element can be the image of many things. Yes, because permutations are resolved. So, see, one thing you can feel is that this problem will not be very difficult, right? It should be possible to resolve. It will not be some open problem or anything. It feels that feeling is there, I think. You have to just make it concrete. Wait, it may still be tricky. Let's see. So, if, for example, we have this. Okay. Now, in a general graph, mm, what do I say? Actually, now I think we don't even need graphs. We can just say it directly. Wait. Yeah, yes. Yes, I know. I didn't write it, but since we got that it's power of 2, we concluded that, right? Correct. Yeah, I understand. Yeah, it's fine. Means it will, wait. Oh, yeah, it will always be a power of 2. Yeah, that we understand. Yeah, correct. Yes. Yes, and now I think now you can sort of feel that doing it for permutations is actually enough. Because you see, if you take a point which is in the range, right, and you look at its pre-images, right, then any invariant set will actually have to include all those pre-images, right? Uh, so, I mean, I should say that invariant subset will never contain one, but if it contains one of the points in the pre-image of one, then it should contain all the points in the pre-image of. Oh no, that's nonsense. That's yeah, that's wrong. Yeah, right. Because then I was thinking of quotienting the domain and making it a permutation, but that doesn't work. Hmm. But okay, I think yeah, we are still close. Let me just go to the next page. Somehow it seems like permutations are enough. S- So I've sort of grouped them according to their pre-images. Some of them might be empty also. Okay. No, it will not always be a power of 2, right? Yeah, I think that is yeah, because you see what is going to happen is, so whenever you're counting invariants, you are like, so from the image set you are taking uh, mm, maybe I should say like like, this is the domain and this is the codomain. Or maybe actually you see, as you understand that the codomain is not important, the range is what determines everything. Yeah. Huh. Hmm. Right, exactly. The first example. It gets to power. Yeah, so it's not always the power of 2. In fact, I was going to. So basically, through this, you can actually enumerate. Yeah, you can actually completely enumerate. Okay, so enumerate what? Enumerate the number of invariant subsets. Okay, but yeah, and from when you looked at, eh, yeah, yeah, in terms of the size of pre-image, you can actually completely enumerate. Because just to give a small example, so you see that only the range is important, and from let's say that the let's say that the range has size m. This is n and this is m, and of course m is less than equal to n because you're taking functions from n to n. And now you see, now what happens is you just choose k things. This m choose k, right? Which means you choose which k things you are going to. So you want to construct an invariant subset. So first you choose k things from the range, right? Uh, because you want to choose you want to take you want to choose from pre-images of these k elements, right? And then basically for every k of them you have to look at the pre-images, right? And then it will become 2 to the, for example, f inverse 1 minus 1, like the pre-image of 1. Let's say this is 1. Let's say you chose 1 to k from the m things, and then from the first one you take the pre-image, that's f inverse 1. So that's going to give you 2 to the f inverse 1 minus 1 choices, because you have to just pick a non-empty subset of that in order to construct your and in this way you have to do this way. You can actually enumerate, and then you have to add this over k. Yeah, I want to m, and you have to stare at this number and see what numbers can be written in this form. And my belief is that all numbers can be written, but because like this m choose k forms a kind of a basis also, right? For Yeah, you have to just look at it. Then maybe you can. But still, the question is unanswered, right? We do not know what numbers you can get. Yeah, but if you do this analysis and maybe you can then tell me what you get. Yeah, or any other analysis is fine. But this is the closed form, so if you take small numbers and maybe you can get some idea. So basically, in the permutation case, this was always 2, because f inverse of anything is 1, and so you were getting summation m choose k, which is 2 to the power m. So that's why, yeah. So that's right, right. So have a look at it and see. In fact, it will go from 0. Yeah. Yes. See what numbers you can get this way. Yeah. I think you should solve this problem. This can be actually an interesting question. You should try to work on this, and if you can get a small result, then it's a good result, right? And you can maybe ask your professors and write it up, and yeah. Anyways, yeah, yeah. But just maybe you have to do some calculations for small cases. Do it, and then I think you can have some idea. Yeah. Okay. Yes. Yeah, so it might be, you may to still spend some time, which I am reluctant to do, but I think this problem is important for you, so you should do it. Okay. Yeah, so these are the things, and let's see if there is anything else. Or maybe we just do some small cases and see. So if I have, it means let's try to, yeah, yeah, and let's try to see if you can get this number 3, right? Because yeah, how, yes. R 2 power k plus 1. Mm-hmm. हाँ, yeah. 3 and 3 to 2. No, does that give me? I mean, I'm unable to see why. No, this gives me 4. Let's see, empty set. Let's see. 1. Yeah. Yeah, let's see. Yes, but now when I uh, put these things, oh, there is a problem. Yeah, this there is a problem with this formula. I think it was feeling like that, right? There is a problem with this formula because you cannot really write f inverse 1 here because you don't know which k subsets are you taking. And this f inverse 1 comes after you have decided upon a particular k size subset, right? Otherwise, this will again be a monstrous summation over the subsets. So you take k subsets and then there'll be a summation over the subsets. This will actually go, yeah, this will actually go in the indexing set. The M choose K will actually become an indexing set instead of, because you're going to sum over the subset. Yeah, so that's, yeah. So and I think that's about as good as a closed form we can get. It seems. It seems. Yeah, and then given a subset, you have that thing. Yeah, some powers. Yeah, this is very strange. Sorry. Let's see. So can you prove that this is an even number? Yes. What were you saying? Hmm. Wait. What is so on? I didn't see the pattern. Oh yeah, okay. Yeah. You want to count the invariants of this? Oh, okay. By the way, this is even, okay. That I figured out. You can just take mod 2 and see that there are even number of terms in the summation, so it will be even. So 3 is, so we can forget 3. It's never going to be. Yeah. Yeah, but now maybe through these examples you can figure out whether it will be power of 2 or not. Let's see. So let's actually do this example. See, it seems like it. I mean, actually, no, I shouldn't say. These summations can be very strange. They are very much, and it can still be a power of 2. Yeah, but so what about this? Let's see. Yeah, right. Uh-huh. Oh wait, no, but this is a bijection, right? So you will again get a power of, yeah, some theoretical results like bijections always give power of 2 and it's always even. We have to, yeah, always use that along with this algorithmic and thing which you are doing, right? Kind of taking cases and, yeah. So it this will for power of 2, right? At least that much we know from theoretical. And huh, yes, yes. And if you actually look at the other extreme case, this also this also gives a power of 2. That might be some bad or whatever good news. Because this is the other extreme case, right? This always also gives power of 2. Okay, okay, wait. Now I think something is there. Yeah, that we said. So in the codomain, the codomain is not important, only the range is important. So we can forget, right? That also we have cleared out. Yeah. Wait, it seems like it will always be a power of 2. No? It's because it seems if you kind of somewhat of convexity, because the other extreme case is also giving the same thing. And this kind of problem looks convex in the sense that it seems like you can account it from the extreme cases. But anyway, yeah. Okay, let's see. Because any function is a sum of these kind of functions in some sense. Some, yeah. Because every time you are creating an invariant, you doing this kind of thing. But let's, yeah. Yeah. 1 to 1, 2 to, yes. Hmm. Yes. Yeah. Correct. Yes. Yeah, so it's basically, I think, comes down to some combinatorial identity kind of thing. This will be a power of 2. One has to just say it in a different way. So this formula is not useful, but if one counts in a different way, one gets a power of 2. Let's do that. Hmm. Yeah. Now, if so, basically that's what you're doing. So you look at the range, but now I think if you look at the fibers, meaning the pre-image subsets, right? And we count. No, I mean, look at the inverse images. You look at, so you take your function, you partition the domain in terms of inverse images, and start counting based on these inverse images. Oh, right. I'm sorry. Yeah, that's what you said. In this particular example, it is that. Yes. Yeah. Right. Right. So now you try to see. So you start your counting by looking at the perspective of these things. Then it's yes, yes, right. That's a good thing that it will be a partition. And really, the order doesn't matter. You can just, right, it's just like this is some 1 up to k1, and then this is k1 plus 1 up to k2. The order doesn't matter at all, right? So it's just a partition. Yeah. Now if I want invariant subsets, these things, yeah, right. So any invariant subset is of course a union of these, right? An invariant subset. No. Yeah. Oh, okay, okay. I think I've been doing many things wrong. You're right. Uh, oh, yeah, your definition of invariance is, yeah, according to that definition, I think unfortunately this formula might also be wrong. Yeah, maybe I had something else in, yeah, wait. Oh, yes, sorry. So then for this function in which everything goes to 1, no. So what are the invariant sets? Huh? Huh? Right. Yeah, so this formula is wrong because it's wrong, because it's kind of counting something else. Yeah, so this is 3. Uh, ha, ha, ha. Yeah. Now the question is, can it be all? Yes, right. Oh. So because there are 2 power n functions, if right, yeah, the n power n. Yeah, yeah. Then yeah. So we have found an example for 3. Now you have to think, right? Yeah. Now you have to try to think about it. I think it's an interesting question. Right. Yeah, that's right. Yeah, so you try to see, or maybe binary expansion, and you can break it and do something. No, because no, I'm just saying that every number has a binary expansion. Maybe you try to use that because you're getting powers of 2s easily. But okay, no, but you're right. I mean, yeah, that is not. It doesn't combine directly like that. Yeah, so maybe this 2 power k plus r might be easier. Maybe some induction or something. Uh-huh. Hmm. Hmm. Okay. Yeah, 2 power. Yeah, the 2 power k plus r might work. Yeah. Uh, permit. Okay, let me think about it. Okay, and you also think about it. It seems possible. Seems possible. Yeah. S- Yeah, it seems possible. Yeah, even with that idea, if this combining this, so if you have a permutation, then you get 2 power m, and then if you send the then if you send the rest of the numbers to up, yeah, to one number which is not in what thing, earlier thing or okay, one goes to two. Okay. Okay. uh, right. Yes, that is what I was also thinking. Yeah, so you send these two so that they don't contribute to invariants. So that, I mean, so it will just become 2 to the okay, I don't know. No, right. 2 3 comma from 3 comma 4. Mm-hmm. Uh, right. I mean, so if it contains 4, then it must contain 3. Yeah. So then it cut. Oh yeah, you have all sorts of options. Yeah. No, but wait. If you take 5, oh yeah, you can take 5. Yes, you can add 5. Huh. Hmm. Okay. From apart from this. Oh yes, that's okay. Yeah, that's plus 3. Yeah. Yeah, and you have taken the empty set and you have taken, yes. This is a complete counting. Yeah. That, and you have counted that. That you have counted in the last 3, and in one of the last. Yeah. It seems like there is might be some way to count, right? Think about it. Yeah. I mean, at least for these examples which you're making, it seems like there should be a way to count, and that way you can, yeah, and that way you can get 2 to the power k plus r, where r is less than 2 to the power k or something, and that will give you all numbers somehow. Think about it and let me know. That is interesting. Okay. Yeah. Yeah. So for now, we have, yeah. Okay.